Okay, so I will try to answer this question again. Will Divya is asking, will these not make some other points misclassified points when the line is moved? Yeah, Divya, you're right. This when the line is moved, this will misclassify some correctly classified points because this line is moved. But according to not according to what the theory of perceptron learning algorithm says is that when you do this operation for every set of every sample misclassified sample, this algorithm will converge. This will converge to the converge to the hypothesis where that hypothesis classified those points very accurately, and it will only happen when your data is linearly separable. What is linearly separable here is these are the points, right? These are the points, and let's say these are the other points. So this, I can separate these two classes by using line. So this is linearly separable. But for an example, I have a data set that is like this. This is this data set. This is this data set. That is not separate, that I cannot separate it by line, then it is not linearly separable. So this perceptron learning algorithm only works for a linearly separable data. Okay. So can we, Ram Kumar is asking, so we have to apply this algorithm iteratively? Yes, sir. You have to apply this algorithm iteratively. And for every misclassified point, you have to do this given operation. That is addition. Will these not make some other? Okay. Varun, but it might be some other points become, yeah, same question, and then adjusting the plane. Yes, to a third, you are taking this tent. Okay, yeah, then how will I have to know? Okay, I'll move to the next slide now. So one iteration of a PLA is W plus WX, that you know what it is. So this Y is nothing but this a plus or minus. If it is, I already explained it in the previous slide. So the iteration goes, pick a point from this to this and run a PLA algorithm. That's it. Just to mention that if you take this point in some different manner, like the order of point matter here, order of samples matters here. So for an example, if this is the line, so there could be million of hypotheses right here in this set. So it depend upon which, sorry, this is not the line. So there are millions of infinite lines here. Infinite lines means infinite decision boundary here, and these decision boundaries may come up with the different orders of this point, how you are taking it from a data set. That's it. That's it. So how do identify the points are linearly separable? So these are the very good questions. So Varun is asking how to identify the points are linearly separable. So yeah, not so fast. This is the first class, and we will cover all these things very slowly. And yeah, we will just take this one. But for now, I can say that it is not possible to have a data set and tell that whether it's a linearly separable or not in a first shot. So this is just an introduction here, and what we are doing in machine learning. So what we are trying to improve the performance of the task with the experiment. Yeah, I already explained that we have a task that whether to approve the credit or not. We have experience. Experience means the historical data for which we have already did that. So we have a label data. Using that label data, we are trying to come up with some hypothesis. And here in this algorithm, we have a hypothesis set. In the previous slides, we have a hypothesis set that are having a lines that are, and there are infinite lines in this set, infinite lines. So here hypothesis set is a set of lines in a two-dimensional plane, infinite lines. So you want to come up with a line that can classify the data accurately, right? So that is your task. So there are two types of there are type of learning: supervised learning, unsupervised learning. So this is an example of supervised learning. I already told you what is classification, what is regression. Classification means when you are trying to classify a given point. For an example, whether I should approve the credit or not. This is a classification problem. I have two classes here, yes or no. Regression means I want to find out, I want to predict the age of a person given a parameter. What could be the age? This is a linear line and it could have an infinite output. For an example, his age could be 12 years, 13 years, and this could be known linear function, or it could be linear function. So we will take these points. Unsupervised learning means that we don't have labels here. How supervised learning is different from unsupervised learning. In supervised learning, we have a data set and we have a label. But in unsupervised learning, we don't have label. We are only having the data that is not labeled. So we try to because this is the problem that we don't have labels. So something we can do. Still, that is not very up to the mark what we do in supervised learning. But in unsupervised learning, we can do clustering. For an example, I have some given. For example, there are number of users in a shopping mall, and I want to find out which are the similar users in a crowd. So for an example, there are 1,000 customers for a shopping mall, and shopping mall want to come up with some offers. So it want to find out similar users in a crowd that belongs to some common characteristic, and there are another set of users that having some other content. Let's say there are 4 clusters in it. So there are 4 clusters in it. Now, when I know that this is the cluster, one cluster, this is the second cluster, and in each cluster there are similar type of user. Now, if I get to know that there is some information, if I get to know this user is liking some T-shirt, is really liking this T-shirt, and because these are the other users which are very similar to this user in a common characteristic. It depends what we use to cluster. So this shopping mall can send the offers to these users on their mobile phones. So this T-shirt is very new arrivals in this mall, and for the other set of users, it can send another offers depending upon how this user is liking or this user liking. So in clustering, if when we cluster, if we get some information by one customer, we can apply that information to other users also in the same cluster. And these semi-supervised learning, reinforcement learning, active learning, we will take one by one. So when we come, it will be more clear when I will come up with one example there. Data is labeled. Yeah, given mail is, I already told you what is this data is labeled here. And supervised learning, unsupervised learning, the same thing. Measure of performance. Yeah, so this is an important slide here. So measure of performance here. For an example, I want to introduce 2 loss functions here, that is 0, 1 loss and square loss. So I come up with some hypothesis, but there should be some way that I can tell that yeah, that this hypothesis, what I come up with is good or bad. So what I can do, I can compare my hypothesis with a given example. For an example, some some points are there, some points were there, right? And somebody asked me to fit a line to these given points. So I I propose one line, and this is this line. Sorry, this is this line. Now, how do I know? There should be some way that I can tell that this is a good fit or not. So this is this is x, and according to this x, this should be the value of y according to this line. But the real value of y is this, and predicted value of y is this. So this is the difference in prediction and true value. Uh, for this point, this is the difference, and this point, this is the difference, and this point, this is the difference. So if I add all these differences, if I add all these differences, and this difference, for example, there are two lines. So I add difference of these points. So I add differences of first line, difference of first line, and difference of second line, difference of second line. So if somebody asks me which line is good, so I will tell according to the comparison of these things. If the difference of first line is less, let's say this is 10 and this is 8, so I will definitely say that the second line is a good fit to a given data set in comparison to the first line. So this is a square loss function, what I just explained. And loss function is I will go one by one. For example, in classification, this is for regression. This square function is for regression, and this is for classification. Now you give me a mail. I will tell you whether this is spam or not. For an example, you give me a mail M1, and I will tell you, yeah, this is spam. But the actual mail was not spam. It was not spam. So here, what I predict is a spam by my hypothesis, but the true level was not spam. So this is a mismatch. So I will count 1 for it. So every time my hypothesis will mismatch with the true label, I will add 1 to it. So this is nothing, but it is the sum of the misclassified samples by my hypothesis. The more this sum is, the more this sum is, the less the sum is, the better my hypothesis is. So why use the square of the function, mean square root, mean square error? Yeah, square error. This is a square error. Why I'm using the square of the function? So square of the function is just for the simple. There are actually big reasons also, but for now you can take it. For an example, this is +1, and this is -1. So +1 -1 will result into 0. So if I will square these two, 1 square plus 1 square, it will be a 2, right? So the square will take care about these absolute values. Okay, so just for a 5-minute break. Thank you, Rakendra. Okay, now it's starting. It's recording. So this is a probability theory. In this example, we are having two boxes. One is red and blue. Other is blue box. So let's say I have one variable That variable is random variable. Random variable means that variable can take any value from a set. So for an example, if B is a variable, it can take either blue or either red. So this B is a variable that can take small r and small b. Small r stands for red box and small b stands for blue box. So the probability that random variable b takes the value small r, that is red, is 0.4. Is 0.4. It means that the probability that this small b will assign to random variable capital B is equals to zero point 0.6. This is 0.6 here. Isn't it should be 0.5? See, this is how I defined it. So don't take it for an example. It could be possible that this red box is little farther than me, and this little red box is placed little farther than me, and this blue box is closer than me, and I am little lazy always. So I will prefer 60% of the time the near box to me, and rather than farther box. So there could be number of things. Don't go into that why it is so. So don't question here why this is that probability until it is like there is some basic reason. So take it like this, that the probability of assigning red box to this random variable is 0.4 and blue is 0.6. So so there are number of points I want to discuss. If now the question, now you can question it. If I am saying once I choose the red box, what is the probability that I will pick apple here? So this is the apple, green one, and this is the orange. This is this is orange, and this is apple. So tell me, if I choose a red box, what is the probability that I will pick the apple here? Because right now you don't have to tell me anything. Right now there is no need to specify anything, because I know in red box there are 8 items. So there are total 8 items, and out of 8 items there are 2 item of interest, that is apple. Somebody come and ask me, if there would be only red box, what is the probability that you will get apple if you just pick one item from it? So the one fruit from it. So the probability that I will get apple if I will have only one box, that is red box, is 2 by 8, because there are 2. What is that? 0.2 by 8, right? So now if somebody gives me only blue box and asks me what is the probability of apple, then it will be 3 by 4. And let's make this problem more interesting. And somebody come and ask me, if I'll have both boxes, what is the probability that somebody choose apple here now? See, at first when I was saying that I was having only red box, then the probability of apple was 2 by 8. When somebody comes and asks me I have only blue box, the probability of choosing apple was 3 by 4. Now I am having both these boxes right now, and somebody come and ask me what is the probability that I choose apple. One by half? No. 5 by 12. Okay. Okay, we'll discuss it further in the slide. I will bring this slide back to the question again. So this is kind of what could be the probability, what could the kind of questions there could be. Yeah, Divya is correct. So it could be in that way. So I will bring. I will discuss this problem in detail when in the coming slides. So first, I will tell you what is joint distribution, joint probability distribution. So joint probability distribution. Let's say this is a table here, and in one side of the table there is x value, and on the one side there is a y value. So this x, if every box that is having 1 by 20 or 2 by 20 or 3 by 20, it is saying that if I come and pick 3 and 3 at a time, 3 for x and 3 for y at a time, then choosing of this pair 3 3 is 3 by 20. If somebody come and ask me what is the probability that I choose 4 comma 1, 4 by x, so for example this is my ordered pair xy, and somebody come and ask me what is the probability that I will choose 4 1. So this is, from this table I can see that the probability is 0. So likewise for every pair there is a probability, and the sum of all these numbers in these boxes should be 1, must be 1, because this is a mass function. This is the distribution, and the distribution means that the integration or sum of all the probabilities in that distribution should sum up to 1. So I didn't check, but I will see what is this table is also having, is filling this condition or not. 1 2 3 4 5 6 7 8 9 10 10. Yeah, I think so. So the sum of all these boxes is equals to 1. So this is a valid joint probability function, mass function. Why there are two notations. You can say this is mass function, and there is a probability density function. Mass means when it is discrete, and density means when it is continuous. So there is a question. So how did we arrive at this table? Again, so let's say this is a given distribution. And somebody come and some customer came to me and asked me that this is the probability we have seen in our business, that every time 4 comes, every time x is 4, y will be 1. I have never seen this pair or set of pair. So he calculated it somehow and it come up with this distribution. This is the table. So now once I have a joint probability distribution and somebody come and ask me what is the probability that y is 1. See, right now I'm having this probability every time, but somebody come and ask me what is the probability of y equals to 1, right? How will calculate it? So you know that probability of y equals to 1 is equals to probability to x equals to 1, y equals to 1, plus probability of x equals to 2, y equals to 1, plus probability of x equals to 3, y equals to 1, plus probability of x equals to 4, and y equals to 1. So if somebody come and ask me what is the probability that I can see the value of y is taking 1. So y can take value 1 with either in these 4 different conditions. I just want to know what is the value of y at 1. But it can take 1 with x1, x2, x3, and x4. But because I am only interested in the value of y, so I can sum up all these probabilities and tell that customer that the probability that you can see, because he come up with a joint distribution and is now interested in asking me what is the probability that I can see y. So I can tell him that the probability that you can see the y is 1 equals to 3 by 20. Right, sum of rows. So this is known as the marginalization of this variable. So here I am marginalizing out the x variable. And so this is also known as conditional disturb. So in row, I'm summing up, when I'm summing up the rows, I'm just marginalizing out or I'm leaving out the x term here. And if I'm saying that what is the value of y equals to 4, what is the probability, then I will sum up the whole row irrespective what the x is taking, because I'm only interested in the value of y. Likewise, I will sum up the column if somebody is asking what is the probability of x irrespective of y. So I will take that, well, for example, somebody is asking what is the value x equals to 2. So irrespective what is the value of y, I will sum up all these columns, 1 upon 20, 2 upon 20, 2 upon 20, and 1 upon 20. I am reading it from top to bottom. Sorry, bottom to top. So it is 6 by 20. So don't, so this is just how you get this table, right? Don't think too much about this, how come up with this table. Somebody gave me this table, right? This could be. So joint probability distribution, what is conditional probability mass function? So the conditional probability mass function is nothing but the distribution, given some condition. For an example, if this, I'm considering this row only here now, this row. So this is a joint distribution, let's say this whole table is a joint distribution. But somebody come and ask me, what is the probability mass function when y equals to 1? So when y equals to 1, what I can do, I can take this probability, and this probability and add them and put them in a denominator, summation. And for each value of x, that is x equals to 1, x equals to 2, x equals to 3. For each value of x, I am putting this value now. For an example, this is let's say 0.2, 0.2, 0.3, and 0.2. Let's say. So I'm just adding all these things, putting into the denominator, and for each value of x, I am putting that x value of x on a numerator and dividing it. I will get some probability. When I add all these probability, I will get again 1. This is a normalization of this. So this is a conditional density. Conditional density is nothing but if your domain is fixed. If your domain is fixed, then you are so intuitively it is like this. For an example, this is my probability of 0.5, and this is of 0.5. This is x, this is y, right? And let's say this is 0.5, this is 0.5. This is a total probability that is of 0.5 in a whole domain. But somebody come and ask me what is the probability of this section given y, and what is the probability of this section given y. Because y is given and this is a probability, then this, let's say this is A and this section is B. So A given y plus B given y should be 1, because the whole domain is y. I am trying to come up with a probability within that y domain. So if y is given, what is the probability of A? If y is given, what is the probability of B? Because y is fixed, y is the whole universe now. Within this universe, somebody is, if could be 2 possible events and y is the whole universe, then the sum of those 2 events must be equal to 1, because it is normalized by the total probability of y. So this is sum of rule. So this is again the marginalization which we discussed in the previous, and this is the product rule. This is joint probability distribution. Joint probability distribution means what is the probability of seeing X and Y. So it is like, so we can say that the probability of X and Y is the probability of X, and the probability given X, what is the probability of Y. So it is like this. For an example, this is X and this is Y, and somebody is asking what is the probability of seeing X and Y together. So what is the probability of X? This is the probability of X. Given X, what is the probability of Y? So I will multiply these two and come up into this domain. This is the product rule. So this is with the symmetry. For an example, P of xy equals to P of X, probability of Y given X equals to probability of Y, probability of X, probability of X given Y, equating these two terms, I will come up with this notation. This is nothing but a Bayes theorem. And this Px is sum of product rule. It is, I am summing it in the denominator. Okay. So this is the same function. We just quickly go through this. Just quickly go through this this thing. So what is the, if B is given equals to B, what is the probability of A? What is the A for means apple, O for orange. If B is given, what is the probability of A? Apple. So this is B, and what is the probability of apple? It is 3 by 4. We already discussed it. Where B is given, what is the probability of orange? It's 1 by 4, and this is a conditional. If you add it, see, this is, if you add it, it will come to the 1. So if R is, if B is R, what is the probability of orange? So it is nothing, that is 6 by 8. And if B is R, what is the probability of apple? It is 2 by 8. And this is what is the probability of orange. So you already know, I know most of the people, this is very, so this probability of orange is nothing but the choosing of my first box, that is red, into what is the probability after red I choose orange, it is by 6 by 8, plus probability of this choosing this blue box, and in blue box what is the probability of choosing orange again. So please solve this and you will come up with what is the probability of apple, like with this. The probability of apple is like point, you know that how to do that. This is the Bayes theorem. The main important thing that I want to specify here is this is the prior probability. This is a prior probability. For an example, somebody asked me, somebody can come and ask me, what is the probability that I can choose blue box or red box? If somebody tell me that there is a belief that you can choose red box with a probability of 0.4, with a 0.4, now tell me what is the probability of choosing a red or choosing a red no. So how can I interpret this equation? So this is a prior probability that somebody come and ask me that the choosing of a blue box or red box equals to 0.4 or 0.6. This is my prior belief. Prior belief means that somebody come and tell me, or there is a reason of choosing in this manner. But now somebody say that I have just seen that I have a fruit that is orange. I have a fruit that is orange. Now tell me what could be the probability of a red box. So there is the prior belief that is zero point 0.4. The choosing the red box is zero point 0.4. This is a prior belief. But somebody come and ask me that I just find out that I just picked an apple, just picked a fruit, and that fruit is orange. Now, what is there any change in belief? Is there any change that is there any change in belief that we have? Is there any change in belief of the probability that we have chosen blue box or red box? So will this observation make any difference? So I will try to explain this point again. So my prior belief was that red is 0 0.4 and blue box is 0 0.6. But somebody come and tell me that I just choose an orange. Will that observation, will that observation will make any difference in my beliefs? I think so. Because intuitively, if you see, there is a very less probability in this box of choosing an apple as orange. But there is a very high probability in choosing an orange, irrespective of how we come up with this box. Because this probability was 0 0.4 and this was 0 0.6 at previous. But somebody come and tell me that I just got an orange. So will there be any change in the belief? So yes, that a person might now tell, and if I will ask somebody to guess now, that I picked an orange, what is now is there any change in probability of picking red and blue after this observation? So he might have an intuitive idea because he chose an orange or he got an orange. There might be high probability in having that. There might having a high probability of choosing that red box. So this is that will change this probability. And if you put this in an equation and solve it, that after observing this orange, the probability that box is red will be greater, whatever this notation is, probability in this case only, probability of red given fruit is orange is greater than probability of box is equal to red. So you just solve it and try to let me know whether it was right or wrong. Probability of range is 0.5. So this is independence probability that P of A comma B equals to independent probability PA into PB. They are said to be independent, and you know this was the formula at first, but if they are independent, this is how we take it. There is no effect of knowing the other of probability. So independent probability can be written as the product of these two probabilities. Right, and the joint probabilities P equals to B, equating these two statements because these are the joint probabilities, and I know that independent probability I can write. I can equate this equation 1 and 2 and I get this probability. This is nothing but, in this case of fruit example, if I say that the proportion of fruits in both boxes are same. The proportion of fruits in both boxes are same, that is blue and red. So if you tell me if you tell me the fruit, that will not change my belief because I know they are independent of each other. So this is probability density in a continuous domain. For an example, you can denote it by a graph, and the sum and the cumulative distribution is the probability so far you have seen. So what is the difference between red and blue? So this is the probability density at this point, at delta x. So this is the probability density at this point. And what is blue? It is saying what is the probability you have seen so far. So this is the sum of this graph. Under this graph, this point is the sum of under this graph. This is a commutative probability. You have seen so many times it. So the general formula is like probability greater than 1, the sum of the probability density function equals to 1 integration, and probability density is always positive. Expectation. So the expectation is probability of x into x. For an example, what is the probability of fair unbiased coin? So I know that the unbiased the probability of head equals to 0.5, and the probability of tail is equals to 0.5. And let's say I denote the head by 1 and tail by 0. So what is the expected number that I get? So because the probability of seeing 1 is 0.5 plus the probability of seeing 0 equals to 0.5. So the expected number I see, the expected number that I get is 0.5. This is the expectation. Expectation is nothing but like on an average what you will get. So if I toss 1,000 times a coin, what is the expected value that I get? What is the expected value that I get? Expected number that I see, that is 0.5. Similarly, what is the expected value of a dice? So let's say there is a fair dice, then the probability of each number is 1 by 6, and the number is 1 plus 1 by 6 plus into 2 plus 1 by 6 into 3, likewise plus 1 by 6 into 6. This is the expected number, and I hope that it will come around 3 point something. Like on an average, what number you will get. Or in a very simple sense, what is the average in a class? For an example, there are 100 students, what is the average number? So you sum up all the numbers and divide it by 100, that is average. At the in probability it is expectation. So variance is how much that number, how much there is a variation, how much each number is deviating from the mean. So this is variance. So this is expected number, like average number, and this is each number one by one. So you are subtracting a particular number from its difference and squaring it and taking the average. For an example, this is x1, x2, x3, and their average is mu. So x1 minus mu, x2 minus mu, x minus 3 mu, square it. So, square it, square it, square it, plus, 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 and divide by 3. This is how we get it. In probability sense, we get this number by this variance. What is covariance? Covariance means that how the two numbers are correlated. For an example, this is x-axis, this is y-axis. If x is increasing, then y is decreasing, then this is negatively correlation. If x is increasing along with x, there y is increasing, then this is positively correlated. And if there is no pattern in it, for an example, change in x doesn't make change in y, then it is zero variance. So this is an example of covariance. As we have very less time, I don't want to go into this example. Please see and we'll discuss it what is. So it is very simple. For an example, 3.2, how I'm getting the expected value. This is the value of x, seeing x equals to the sum of this row, that is 0.5. Seeing of x equals to 2, this is sum of the row, which is 0.5. What is expected value of x then? 0.5 into 1 plus 0.5 into 2. That is nothing but it's like 0.5 plus 1 plus 1 equals to 1.5. That is 3 by 2. So how this is likewise, this is the expected value of y equals to 1 x. This is the value of y equals to 2 y. This is the probability of y equals to 3. Multiply it by 1, multiply it by 2, multiply it by 3, and sum it. You will get the expected value, that is 2. And this is how you will calculate a covariance. So I'll just take another 5-10 minutes, and I will finish this So this is a normal distribution. In normal distribution, we have average mu here. This is a mu, and the variance, how much it is scattered from the mean, is defined by variance. So this is the variance, how much it is. So if variance is large, then it is more flatter. If variance is less, then it is more peaky. And mu means like what is on an average. What is on an average is this value of x. For example, x equals to 9 here and 4 here. The average value of these 2 points only. 9 and 4 is equals to 9 plus 4 divided by 2. It's equals to 13 by 2. Something like that. So I am just summing up all those x's and dividing it by. So I will get this x mu. And the integration of this, because this is a distribution, and for distribution the integration must be 1. So then decision theory is nothing but like for an example, if you want to calculate you want to ask me to calculate some number, so some probability of a given class. For an example, you gave me some x and ask me to find out what is the probability of spam given this mail, and what is the probability of not spam given this mail. So I will calculate that this is a probability. Let's say this is 0.4 and this is 0.6. Now I have to judge it. I have to decide it. What is this mail? So decision theory is nothing but it is saying that wherever you find out the minimum risk in guessing the right class, you take that one. So here the probability is 0.6 is higher than this probability. So my chances of correctness is greater in this case. So I will guess that mail equals to not spam. Okay. So minimizing the misclassification rate. So misclassification rate is so what is misclassification? So for an example, this is a risk. This is a risk that I'm calculating here. What is the risk that overall so my risk is, for an example, these are the two distributions. These are the two distributions. And somebody asking me what is if this is the decision boundary. If this is the decision boundary, what is the risk here associated with it? So if this is a decision boundary, and here I will always say that this is a class 2, and here I always say this is a class 1. So what is my overall risk? Because I'm in this, I'm saying that this is my class 2. But here in this region, I'm saying this is my class 1. But you can see this is the probability that belongs to class C1 region, but this probability is saying that this point belongs to C2. So this point I'm talking about, let's say. So if I check this point, so this point is nothing but belongs to, this probability of belongs to class C2 is this, and this point of belonging probability to C1 is this. But I decide my boundary here. This is my boundary. So without caring about these probabilities, I am just clearly deciding that this point belongs to C1 region. Now, how much risk I have taken in deciding this point to C1? Because this is my probability C1. And so I will add all this area here, because this area is misclassification of C2 class, because I have classified it C1, but this area belongs to C2 class. And here, this graph, this is actually belong to C1 class, but I misclassified it to C2. So this area plus this area, because this area also belongs to this area and this area. Yeah, this area and this area. So I want to minimize this risk. When I want to minimize this risk, I have to minimize this area, this given area. And to minimize this area as nothing to maximize the correctness of that. In dual form, if I want to maximize it, this is given here. So in the crux, I can say I can always minimize my risk if I classify every time the point with the higher probability, right? So these two problems is nothing but the same, but the perspective is different. Here I am minimizing the risk, and here I am maximizing the correctness. So the crux is every time I want to minimize the risk. It means that I want to maximize the correctness. I can maximize my correctness only when I will assign that given point with a higher with a class with a higher probability. We'll discuss it again in some other classes, like in next class also. Thank you.